All right, so this example is a different one that's in the book. I like to sometimes give a variety of it. Well, just examples. The examples in the book are very good, but if I can provide, you know, a different example, it gives you a little more variety. So take a moment to copy this example down. We're going to compute flux, some flux here. Okay, so we have this fairly simple vector field given by y times j minus z times k. And we want to find, and let's pretend like this is hold on here. One moment here. Yeah, so let's say that this is the vector field is describes the flow of fluid moving through a closed surface. And the closed surface, it doesn't have to be a closed surface, but in this case, I'm having a closed surface. Closed surface S is formed by the paraboloid. One is a paraboloid. One surface is the paraboloid y equals x squared plus z squared. Okay, for y is greater than or equal to 0, less than or equal to 1. And the other surface is x squared plus z squared less than or equal to 1 when y equals 1. Okay, and we're assuming outward orientation. Okay, so this surface S will just equal the union of surface 1 with surface 2. So what might be a nice way to start this problem off? What would be helpful to have? Well, how about a picture, right? All right, so let's go ahead. Are we good? May I move to the next page? Okay, John's good, and Ryan's good. And Eric's good. Very good. So, and Robin's good. All right, well, let's go to the next page then. So here's a picture of my surface. And again, my surface S consists of the union of the two surfaces. Now the first surface is the paraboloid, okay, and it goes out to y equals 1, and the second surface is this disk located at y equals 1. Okay, so let me give you a moment to copy the example down, or the picture down. Let me know if you have any questions. Okay, now let's see here. Hold on, there was a chat here, came through. Oh, yes, let me see here. Alexander caught a typo here. Okay, this class should be, thank you. This here should be an RZ. Good catch. Thank you, Ryan. So, okay. So, well, all right. The parameterization of the paraboloid, okay, we know that for the paraboloid that y equals x squared plus z squared. We know that. That's true. Okay, that defines the paraboloid. So then just let x be x and z be z. Okay, and okay, and also, well, we know also that x squared plus z squared would, you know, what are the constraints on these values of x and z? Well, the constraints on the values of x and z are that x squared plus z squared would always be between 0 and 1. So, okay, that's fine. Well, all right, we're gonna do the cross product now of Rx and Rz, those derivative vectors. And when I do the cross product, I'm going to get 2x times I minus 1 times j plus 2z times k. So nothing you haven't done before. You've taken cross products. But we have to be a little bit careful here. We have to be a little bit careful. The the cross product, well, so in the formula for the flux integral, we have to take the cross product of the derivatives of the parameter the derivatives of the parameter vector. But I could have just as easily done R of z cross R of x. I could have done the cross product in that order. But instead, I chose the order Rx cross Rz, because that's going to ensure outward orientation. Now, why would that be? Why would that be? So outward orientation, remember, is when our normal vectors are pointed outside the surface. But the cross product, Rx cross Rz in that order, which is equal to 2xi minus 1j plus 2zk, that's going to ensure outward orientation. Okay, we need the cross product of these two derivative vectors to point outward from the surface. Why does that ensure that it's going to point outward from the surface? What special quality? If you look at the surface S1, look, I'm focusing now on surface S1. Okay, I'm focusing on surface S1 here. Maybe I'll put it in blue. And I'm focusing on the cross product of the derivative vectors. What ensures that this cross product vector is oriented out from the surface? Which of the components here can you tell quite easily that's going to be true? The 2x, the -1, or the 2z? Look at the surface S1, the paraboloid, and think about 2xi minus 1j plus 2zk. How do I know that that has outward orientation, that cross product vector in that order, Rx cross Rz? Ryan's correct, and I'm not saying, Eric, Ryan's definitely right. The -1j. -1j with respect to the x-axis, or the y-axis, I should say, does that point to the left or to the right? -1j. With respect to the y-axis, does -1j, it points to the left. That's right. So if I were to pick a point here, any point on the surface, okay, and draw the cross product vectors, the Rx cross Rz, I should say. Well, those vectors, depending on what, I want to be a little careful here how I draw this, but let me just focus, here. Here I am. So x, well, we're in the this surface is sometimes the x coordinates are positive on the surface, sometimes the x coordinates are negative on the surface, and same with the z coordinates. But the fact is that the -yj ensures that, let me just see here. So like for this front part of the surface, maybe above the xy plane, where x is positive and z is positive, but j is -1, okay, that means like for this, Want to be a little careful here. Hold on. You know, so that vector there, which for instance, that vector there, which is the cross product of Rx and Rz, those derivative vectors, that cross product vector points up a little bit, okay, points in the positive direction of the x-axis. Okay, I could maybe draw it a little better. Let me try it again. Come on. Give me my thing here. Yeah, that's better. Now I'm I haven't normalized it, right? But that would be Rx, for instance, cross Rz, that cross product vector, when we're above the xy plane, and the surface is above the xy plane, and we're in where x is positive and y is positive. The point is, so any vector, by virtue of the fact that the j component is negative, means the vector has to point out of the paraboloid, because the paraboloid, the surface, is well, it just has to, it's pointing out from the paraboloid. Okay, is that okay? Are we good with that? Are there any questions on that? Okay, Eric's comfortable. Who else is comfortable? Okay, Robin is wonderful, and John is excellent. All right, so whenever you take the cross product, you don't just take the cross product of, you got to check that the cross product is in the right orientation so that you have outward orientation. And if it turns out you have inward orientation, just take the negative of the cross product. Okay, that being said, let's move forward here. That being said, now we want to find the flux across the surface S1. So here's the formula that we derived in section 13.6. The flux integral is just the double integral over region D, and we know that's going to be a circle, of the dot product of F with the cross product vector. And I write, of course, the vector field F is going to be a function. The coordinates are going to be a function of the parameter vector, or the vector with the vector that traces out the surface, the vector R, and then you got the cross product of the derivative vectors there. And for ease of reference, I note that the vector field F equals yi minus zk, and R of xc, the vector of parameters x and c, is just given there. And then that helps me identify the f of our vector, the f of our field. So the field has components, j component y and k component negative z. So I just replace the I just for y here, I just put in x squared plus z squared. I might as well, because I'm going to be integrating this with respect to x and z, and y equals x squared plus z squared. And then the third component is just negative z by virtue of my definition of my field. Okay, and so when you do the dot product, you're going to get negative x squared minus c squared minus 2z squared. And that can be expressed as the negative quantity x squared plus z squared minus 2z squared. Okay, and I left some work out here. I left some work out, obviously, but in the end, you're going to get negative pi. Okay, let me give you a moment to copy that down. Okay, all right. So flux is negative across that paraboloid surface, and that makes sense because that makes sense. Now the question is, why does it make sense? Okay, why does it make sense? Okay, so look at the vector field. Look at the vector field here. Okay. The vector field is yj minus zk. Now, the entire paraboloid, if we go back to the picture here, okay, and again, here's the vector field, here's the flow. Across this entire first surface, all the coordinates on that surface are the y values positive or negative. If you think about the coordinates across this surface here, every coordinate, that's y coordinate is positive. Okay, good. That's right, Ryan. And below the xy plane, the z coordinate is negative. Well, no, above the xy plane, the z coordinate on the surface is positive. But the vector field has a negative z. And below the xy plane, the coordinates on the surface have negative z values, but the vector field has a negative z, so that's positive. So the point, what I'm trying to say is that, let me just say it the way I want to say it here. The vector field flows inward to surface S1, into that paraboloid. So I mean, just it's really quite simple to see it, but the vector field, because it equals y times j minus z times k, the flow of the vectors, if you were to superimpose the vectors over that surface S1, that paraboloid, the vectors would be flowing in to the surface, inward, not outward, inward. Okay, does that make sense? Are there any questions on that? Okay, who feels okay with that? It'd be nice to get a few responses. Okay, John's good. I mean, this is the field, right? This is the field vectors are doing this. This is what the field vectors are doing. Eric's good. The field vectors are doing this. Okay, if you were to draw the vector field F, that's what those vectors are doing. They're flowing inward to the surface, and that's why the flux or flow rate is negative. Okay? All right, let's continue on. Let's continue on. Now let's look at the second surface. The second surface is that disk. That disk, so here, let me just remind you here. Here's the second surface, right? Right, there's the second surface. That's the disk located at y equals 1. If we parameterize that disk, and again, I always like to use parameterizations of my surfaces because then I only got to worry about using one formula. I don't got to worry about formulas with, you know, just different. I mean, for those formulas where you have a graph of x and y, they're going to change, right? If you have a situation like in this case, like for the surfaces S1 and S2, you have your graphs are a function of x and z. So that's going to change the formula where where the formula is a graph of a function. The function can be written as a graph of two variables. That's going to change depending on what your variables are. And I just don't like having to figure out what the changed formula is. I can always use the same formula if I write down the parameterization of my surface. And that's what I'm doing. So the parameterization of surface S2, that's the disk at y equals 1. Well, y always equals 1. Okay, and then x is x and z is z. And again, here is the limitation on x and z. It can be shown that the cross product of rz cross rx equals 1j. Now you notice I didn't do rx cross rz, because if I were to do the cross product of rx with rz in that order, what would that give me? If rz cross rx gives you 1j, what would rx cross rz give you? Negative 1j. That's right, Robin. Negative 1j. Okay, and so that's fine. That's fine. But if you look at the, and I'll come back to this page. If you look at your surface S2, is outward orientation for surface S2, that surface, is that to the right or to the left with respect to the y-axis? It's to the right. That's right. And so the j vector points Positive j points to the right. So you just have to be very careful when you apply these formulas, when you do that cross product, to make sure that the cross product is going the right direction for you. And if it isn't going in the right direction, just take the negative of it. Okay. So this means then that the flux across surface S2, okay, so, you know, I do the same thing. Okay, same formula, same formula. Of course, the y equals 1, right? Z is negative. I mean, the third component is negative z based on the force field vector. The x component is 0. Okay. All right. Let me know when you're ready to go to the next page. Let me know if you have any questions. Okay, I saw a chat there. Hold on. Okay, Ryan's ready to go. Okay, maybe I'll get a few more chats here. Okay, all right, then let's go to the next page. So now we just compute the flux. And in this case, the flux is positive across that surface because the fact that the field, to the right of the XC plane, the field, the vector's got to go to the right. That goes right with the outward orientation of the second surface, and so you're going to get a positive rate. Okay, so take a moment to then copy down up to here. Let me know if you have any questions. Okay, and so the total flux then, just like with line integrals, I mean, total flux, you just add the flux, the two fluxes, and the net rate of flow of this vector field through the surface is going to be 0. All right, are there any questions on this? On what you just learned here? How many feel reasonably good? Excellent, excellent. You know, these concepts are, this is wonderful. I'm very happy. I wanted to pick a good example, and it seems like this was a nice example. So, all right, and for your section 13.6 homework, which is due next Tuesday, I tried to make sure there's for maybe all or most of the problems, there are some watch videos, some help aids, just to kind of, because this is going to take some time, but this is extremely important. You know, for the final exam, this is going to be very, very important. And the final exam, and let me stop the recording here.